This 17th online lecture session of the course Engineering Thermodynamics. In our previous lecture, we have completed our discussion on the first law of thermodynamics for both closed as well as the open systems. And after that, I have started our discussion particularly on the topic limitations of first law of thermodynamics. Okay. So, in limitations, what we are having, we have seen that first law of thermodynamics particularly deals with the quantity of the energy and it doesn't gives any information about the quality. And another important point, we have seen that first law of thermodynamics is only associated with the conversion of energy, with the magnitude of conversion of energy. However, it doesn't tells us any information about the direction of the process. Okay, so for example, I have given you an example that if we are having a hot coffee cup in a cold room, so heat will be transferring from the coffee cup to the room and the temperature of the coffee will be actually decreasing. But at the same point of time, we cannot say that if same amount of heat can transfer from cold room to the hot coffee cup, because heat does not flow from substance having low temperature to that of high temperature. Okay, but as per the first law of thermodynamics, this statement is also like not wrong, because in this case what will be happening, it is only the heat which will be transferring from the surrounding to our system as a coffee cup. Okay, so as a general, if I talk about, I can say that if I have some temperature source having temperature TH and one another temperature source having temperature TL, and say TL is less in comparison to TH. Okay, so now in this case, what will be happening? We may have the transfer of heat. We may have transfer of heat particularly from high temperature to low temperature. So in this direction, we may have flow of heat. However, if I have to transfer the same amount of heat in the opposite direction or any amount of heat in the opposite direction, so that particular process is not possible. Okay, so this reverse is actually not possible. However, if we are talking about the first law of thermodynamics, so in case of first law of thermodynamics, if we say that say some Q amount of heat is transferred from low temperature to high temperature, this low temperature body will be suffering the loss of Q magnitude and high temperature will be suffering the gain of Q temperature. Okay, so that is perfect as per the law of conservation of energy, because first law of thermodynamics is nothing but law of conservation of energy. So if we are saying that this reverse direction heat is actually flowing, which I have represented with the dashed line, and I am saying physically which is not possible, but for the moment if we consider that it is possible, in that case what will be happening, this low temperature substance will be suffering the loss of energy by magnitude Q and high temperature will be suffering the equivalent gain of energy. Okay, so in this case what will be happening, though we will be having conservation of energy, means first law of thermodynamics is actually satisfied. However, this particular process is not physically possible. Okay, another example I have given you yesterday, so it was about the pedal wheel. So I told you that if we are having some insulated system and initially say it is at state 1 and now we have some pedal wheel over here, and this pedal wheel is having some pulley, and over this pulley we are having some weight which is mounted over here. Now if this weight is actually traversing through height h, okay, so it is basically moving vertically down and it is traversing through height h. In that case, what will be happening? We will be having some work done. So while this weight will be moving down, this particular pedal wheel will be rotating. Okay, so in this case now what we will be having? We will be having change in potential energy, so equal to mgh corresponding to this weight. So this much work will be done on our system due to the pedal wheel. Okay, so while pedal wheel will be doing this much work on the system, so in that case, what will be happening? In this particular case, what will be happening? Okay, so after addition of this much amount of work into our system, if say I conclude that U1 is my initial internal energy of the system, so after mgh work is done on this system, and in that case what will be happening, I will be reaching to some another thermodynamic state 2, and corresponding to say this thermodynamic state 2, I have U2 as my internal energy. This internal energy will be actually increasing. Okay, so if I say that this internal energy has increased, so my U2 will be greater in comparison to U1. Okay, so U2 will be greater in comparison to U1. And by what amount it will be greater? So basically, if we try to see, U2 minus U1 will be nothing but equal to mgh. Okay, so now in this particular case, if you see, this pedal wheel work has done some h amount of this weight has moved through some height h, so corresponding to that change of potential energy is mgh. So because of this, actually our pedal wheel has rotated and it has imparted certain energy to our medium inside. Okay, so because of that, we have seen that our internal energy of the medium has increased, and this internal energy of the medium will be increasing by equivalent amount of the work done on the system. So this mgh over here is nothing but our work done on the system. So if this is work done on the system, so it means this work is nothing but a negative work. Okay, so this is one important point you have to see over here, that what we are doing in this pedal wheel, actually we are doing some work on the system. So that's why we are getting nothing but negative work. Okay, now if I have to say, make this process as cyclic. Okay, so if I have to make this process as cyclic, now we have seen that we are having transformation from state 1 to state 2. Now what I have to do, I have to once again go to state number 1. Okay, so that is something which I have to do now. Okay, so we have seen that while we have added the work equivalent to that of mgh amount, okay, so upon the addition of that work, we have seen that our thermodynamic state is changing from state 1 to state 2. Okay, so we are having U2 as the new internal energy which is greater than U1, and we are saying that U2 minus U1 equal to mgh is the work which is done on the system. As this work is done on the system, so that's why this will be nothing but our negative work. Okay, now what I'll be doing, if I have to operate this process in a thermodynamic cyclic manner. Okay, so if we have to operate in thermodynamic cyclic manner, what we have to do, I have to convert, or I have to shift this system once again from state 2 to state 1. Okay, so how I can do? So initially I had considered that my boundary of the control volume is nothing but insulated. Okay, so that's why whatever the work was done on the system, that is reflected in terms of increase in internal energy. So at this state 2 was our boundary as insulated. So because of that only, we are having now increased internal energy content. If we are having increased internal energy content, obviously our temperature will be more, and we are having different thermodynamic state. Okay, so now if I have to go back to the same thermodynamic state of our working medium, what I will be doing, now I am at state 2, and corresponding to state 2, my internal energy is U2, which is greater than U1. Okay, so now if I have to once again go back to state 1, so I have to do certain process. So what I will be doing, I will be actually transferring now some amount of heat outside the system. So now instead of having adiabatic wall, I will take diathermic wall. Okay, a wall which can interact heat with its surroundings. So I will be sending Q amount of heat to the surrounding, and that Q will be nothing but equal to equivalent to that of mgh. Okay, so if this Q amount of heat which is going out of the system, which is equivalent to the amount of work which is done on the system, so in this case what will be happening now, we will be having actually, we will be once again reaching to the thermodynamic state where internal energy of the medium is nothing but equal to U1. Okay. Now, if you talk about this heat transfer is actually also going out of the system. So, while this is going out of the system, it means this is once again a negative heat transfer. Okay. So, it means that whatever this pedal wheel system we have taken, if we have to operate this pedal wheel system in a cyclic manner, if we have to operate in a cyclic manner, what we have to do? We have to do negative heat transfer and we have to do negative work done. Okay, so when we are doing negative heat transfer and negative work done, in that case only it is actually behaving, or it is completing a thermodynamic cycle. Okay, because first we have gone from state 1 to state 2 by having negative amount of work, then we have some heat transfer from system to surrounding, so we are having some negative amount of heat interaction. So because of that, once again our system has returned from state 2 to state 1. Okay, now if I take the reverse of this system, so reverse means if instead of negative I provide positive heat transfer. Okay, so means I have once again pedal wheel, and let me consider that now my state 1 is nothing but when our weight was at the lowermost position. So when the weight was at bottommost position, corresponding to that our weight is W. Okay. Now if I add some Q amount of heat, so my state, this is my thermodynamic state 1, corresponding to which our energy was, internal energy was U1. Okay. Now what I am doing, I am saying that I am adding a certain amount of heat Q. So if I add Q amount of heat, what will be happening? My pedal wheel position is remaining as it is not changing. Okay. However, our thermodynamic state will shift from state 1 to state 2. Why? Because we have added the Q amount of heat. So if we are adding the Q amount of heat, because of that addition of Q amount of heat, we will be having internal energy U2, which will be greater than U1. Okay, and U2 minus U1 will be nothing but equal to amount of heat what we have added. So in this process now, if you see, the amount of heat added is nothing but positive. Okay, so we are adding positive amount of heat to our medium. But now what I want to do, I want to now bring this system once again to the initial state. Okay, so what was my initial state? My initial state in this particular process would have been whatever the process I started in my earlier case. Okay, so I have some insulated system and this weight is actually at the topmost position. Okay, so this will be coming when our internal energy of the system will be exchanging, doing energy interaction with the pedal wheel, and because of that internal energy, pedal wheel has to rise. Okay, but we know that this process is actually not physically possible. So it means if we are allowing this particular internal energy, so if we are allowing this particular internal energy to have interaction with the pedal wheel and then raise this W amount of weight from bottommost position to topmost position, so that is something which will not be possible. Okay, so as this particular thing is not possible, so because of that, what will be happening? Because of this, we cannot now go back to the first state, initial state. So it means if this is possible, in that case we would have get work done by the system. Okay, so work done by the system is nothing but positive work. Okay, so it means from this particular example, we can conclude that we cannot operate a thermodynamic system in a cyclic manner by just having the knowledge of only first law of thermodynamics, where we are having both positive heat and work interactions. Okay, so that is one very important point. So from the previous slide, we have seen that we were able to operate the system in a cyclic manner by having negative heat and negative work interaction. Okay, however, if we try to have positive work and positive heat interaction, we cannot operate our thermodynamic system in a cyclic manner. Okay, so that is something which we are seeing as the limitation of first law of thermodynamics. Okay, now this limitation of first law of thermodynamics has given origination to a few more systems, and these are the systems which facilitates the feasibility of the processes which are not possible naturally. Okay, so such systems we call as nothing but our heat engine, and similar system is refrigerator. The objective is different, however the mode of operation is almost same. Another system we can call as nothing but our heat pump. Okay, so heat engine, refrigerator and heat pump, these are the devices which allows us to operate in cyclic manner. Okay, so to operate the systems in thermodynamic cyclic manner and to achieve a few processes which are not physically possible. For example, heat engine allows us to convert heat into work, and that too we can operate this particular heat engine in a thermodynamic cyclic manner by having positive heat and positive work interaction. Okay, so that is the actually function of the heat engine. Then if we talk about the refrigerator and heat pump, in case of refrigerator and heat pump, what will be happening? These will be allowing us to transfer the heat from a system having low temperature to a system having high temperature. Okay, so these are the functions which we can achieve with the help of these three very important devices: heat engine, refrigerator and heat pump. Okay, but before going to the discussion of heat engine, refrigerator and heat pump, let me first discuss a concept of thermal reservoir. So thermal reservoir is a very important concept which will be employed everywhere while we will be talking about heat engine, refrigerator and heat pump. Okay, so what we are having, thermal reservoir will be nothing but as we are having in case of a water reservoir, we say that if we are having a body of infinite amount of water, and from this body if we are taking out some finite amount of water, and if it is not changing the amount of water in that body, so change in amount of water is insignificant, so that is nothing but kind of, we can say that it is a reservoir of infinite capacity. Okay, so similarly we will be defining our thermal reservoir. So we will be saying that thermal reservoir is nothing but system or where if we are taking out some finite amount of heat or energy from that particular system. So mostly from the thermal reservoir we will be taking out energy in the form of heat energy only. So we can say that thermal reservoir is a system from which if we take out some finite amount of energy, its temperature will not change. Okay, so it means thermal reservoir is nothing but some system of infinite heat capacity. So this is a system of infinite heat capacity. So the meaning of infinite capacity is that if I take certain finite amount of heat, if I take out finite amount of heat from this particular system, its temperature will remain unchanged. Temperature of this particular system will remain unchanged. Okay, so that is the characteristics of this particular thermal reservoir. So this will be happening. For example, if you talk about your ambient, okay, so many times we add certain amount of heat to the ambient, or we take out certain amount of heat from the ambient. Okay, but as a whole, if we talk about the temperature of the ambient is not affected by whatever the finite amount of heat interaction we are doing with our thermal reservoir. Okay, so that is something we can say that a system of infinite heat capacity. Okay, so now what will be happening? For example, if I have, so what I am basically saying, we know that our heat transfer is nothing but equal to mc into delta T. Okay, where delta T represents the temperature difference and C is heat capacity and M is mass. So there can be two possibilities. Either so heat capacity is nothing but the product of M into C is something which is referred to as heat capacity, because this represents that how much amount of heat has to be required in order to change the temperature. Okay, so if either my M is infinite, if M is infinite, so obviously infinite amount of heat will be required to change the temperature. So in that case, if we are either adding or removing some finite amount of heat, our temperature of the system will not be changing. Okay, or another parameter is C. So if M is having some finite value, in that case C has to be infinite. So if any of these two quantities are infinite for any system, that particular system can act as nothing but a thermal reservoir. Okay, so now what will be happening? If I see a phase change substance, okay, so for example, I have nothing but a saturated vapor. So if from this saturated vapor I take out certain amount of heat, and if this amount of heat is nothing but equivalent to latent heat of vaporization, okay, so if this amount of heat is nothing but equal to latent heat of vaporization, in that case what will be happening? We will not be having any change in temperature. Okay, so in this case temperature remains constant. So it means our phase change substance within the liquid vapor dome can be considered as a thermal reservoir. Okay, similarly, if I have a saturated liquid initially, and now if I add equivalent amount of heat which is similar to latent heat of vaporization, so in that case also our temperature will remain constant. So it means our phase change substance two phase region, if our heat whatever we are taking out or we are adding, if that is within the, if that heat is within the regime of latent heat of vaporization, in that case what will be happening? In that case our temperature will be remaining constant. So for that particular limit where temperature is remaining constant, we can consider this system as nothing but our thermal reservoir. Okay, one of the additional example I would like to include over here. So we are having a furnace. So in many cases we are having actually furnaces. So what we do in a furnace, actually we try to add some amount of air and we try to add some amount of fuel. Okay, so we are actually adding some air and fuel, and then products of combustion actually we are utilizing. So from here I'll be getting some products of combustion. So what we do, we utilize the heat carried by these products of combustion to heat our system. Okay, so whatever the products of combustion will be leaving out of the furnace, obviously during the combustion process, chemical energy of the fuel will be released and that will be converted into heat energy. Okay, so we will be having the products of combustion which will carry significant amount of thermal energy. So if we employ that thermal energy to heat our system, so that will be actually acting as nothing but thermal reservoir to our system. So what we do in case of a furnace, we add the air and fuel at some particular rate, and the rate at which heat is being released, if at the same amount of rate we are removing the products of combustion, in that case what will be happening? The total heat inflow to the system and the total heat outflow from the system will remain constant. If heat inflow and heat outflow are same, in that case what will be happening? Our temperature of the furnace will be constant. Okay, So temperature of the furnace will be remaining constant. So this temperature of the furnace will be remaining constant only if we are operating this furnace in a steady state manner. Means whatever the amount of air and fuel we are adding, so because of that, whatever amount of energy is released, we are removing that energy with the help of products of combustion at the same rate. Okay. So that is something what we try to do in majority of our heat addition system. So when we are adding heat to our thermodynamic system, we generally do with the help of these furnaces. So where fuel provides the energy and we try to take out that energy at the rate at which fuel is providing the energy, and we are having temperature of the furnace as nothing but constant. So I can consider this furnace also as my thermal reservoir. Okay. Now we may have two types of thermal reservoir. So one of the thermal reservoir is considered as heat source. So a thermal reservoir which provides the heat. So for example, if a system is having high temperature and this system is allowing the heat to transfer to some another system at low temperature. Okay, so and upon taking out this Q amount of heat, if temperature of this particular substance is not changing, so it is remaining constant at TH, I can call this as nothing but my heat source thermal reservoir. Okay, and we have certain systems which are maintained at low temperature. Okay, and what we do, we add some Q amount of heat to this system, and if upon adding the Q amount of heat, their temperature is not changing, so it is remaining same at TL value, we call this type of system as nothing but heat sink thermal reservoir. Okay, so we call the system a thermal reservoir which adds the heat, we call it as heat source, and a thermal reservoir actually which takes the heat, which absorbs the heat without changing its temperature, we call that as heat sink. Okay, now let us try to see the principle of heat engine and the operation of heat engine, how it operates. So what I am saying, I have already told you that heat engine is a device which will make possible, so this particular device will make possible to operate a system. This will help us to operate a system in thermodynamic cyclic manner. So this is a system which will help us to operate. So heat engine will make possible to operate a system in thermodynamic cyclic manner and have positive heat and positive work interactions. Okay, so it means our heat engine will facilitate that we are having positive amount of heat transfer. It means heat is added into the system and positive amount of work which we are obtaining from the system, and at the same point of time we can operate this system in a thermodynamic cyclic manner. Okay, so let me give one example. So what I'll be doing, say I'll consider initially a piston cylinder device, and this cylinder is having some additional stops which are fitted in this particular cylinder, and between these two set of stops, we are having our piston, say, initially located at the bottommost position. Okay, and now what we have some gas inside. Corresponding to this, let us call our thermodynamic state of the system as nothing but state 1. Now, after this, what I have done, I have the same system. Okay, and in this particular system now, what I have done, I have actually made this system to contact a thermal reservoir of higher temperature. Okay, so what I will be doing now, I will be making this system to have physical contact with a heat source. So I have a heat source, I have made the contact of this gas now with heat source. Okay, so now while this gas will be having contact with the heat source, we will be having some Q amount of heat which will be released to this system. Now we are considering, say, whatever our piston we are having, on the piston, say initially we were having some W amount of weight. So obviously here also we will be having some W amount of weight. So at this point, so this is my state 1, and immediately after the state 1, what I have done, I have actually brought this system in contact with the heat source. Okay, and this heat source is having high temperature in comparison to the temperature of the system. Okay, so now what will be happening over here, due to this particular heat source, Q amount of heat will be transferring to the gaseous medium, and because of this transfer of the heat, you can see that we are having only W amount of weight on the piston. So if we are having W amount of weight, it means pressure is remaining constant and we are adding more amount of heat. Okay, so upon the addition of the heat, what will be happening? Our piston will start moving in upward direction. Okay, so once again, we have the same arrangement, but what has happened, instead of remaining at the bottommost position because of the addition of the heat, now our piston has actually started moving in upward direction, and while piston is moving in a upward direction, it is raising actually W amount of weight. Okay, so once again we have over here nothing but heat transfer, and now our this entire thing will be actually filled with the gas. Okay, and let us consider that after some duration, so in this particular case also I have the contact with the thermal reservoir, so it means heat is being added to the system. Okay, now after some time we will be finding a situation that our piston will be at the topmost position. Okay, so our piston will be at topmost position. So piston will be somewhere over here, and while the piston has come to this topmost position, it has raised W amount of weight. Okay, and now our entire medium is actually filled with this gas. So this is my nothing but, at this particular point, I will once again make this wall as my adiabatic wall and I will stop the contact. Okay, so now at this particular point, you can see that once again our heat transfer is becoming 0 because we are making the wall as adiabatic. Okay, and during this process, what has happened, while the system has changed, so now we have got some another equilibrium state of the system. So this another equilibrium state of the system we are calling as nothing but state 2. Okay, but that too, what we will be doing before removing this heat transfer, we will first remove this W amount of weight. So now we will take this W amount of weight. So if I take out the W amount of weight, what will be happening? This will be my state. So my piston is at this topmost position. However, we are not having any weight now acting on the system. Okay, and inside I have gas, and this let me call as nothing but my thermodynamic state 2 of the system. Okay, because now whatever the process we had to do, that we have completed. Okay, so now in this process, what has happened, if you try to see, from state 1 to state 2, we have added certain amount of heat to the system. So let me say that I have added nothing but Q1 amount of heat to the system. Okay, now whatever the amount of heat I have added to the system, that is nothing but my positive heat which we have added to the system. Now because of this heat transfer, while the piston was moving in upward direction, piston has raised W weight. Okay, so if piston has raised W amount of weight, it means our system has done some work on the system. Okay, so work is actually done on the system. So say W amount of work is actually done by the system during the change of state from 1 to 2. So this work will also be nothing but our positive work. Okay, now what we want to do, we want to operate this system in a thermodynamic cyclic manner. So if I have to operate this system in a thermodynamic cyclic manner, once again I have to change my state from state 2 to my initial state 1. Okay, so what I'll be doing now, what I will be doing, I will take once again over here my piston cylinder arrangement, and my piston now is at the topmost position. Now what I will be doing, I will make over here the contact of a heat sink. Okay, so what I have done now, I have connected one heat sink over here. So while we are having a heat sink over here, what will be happening? Now we will be having some transfer of heat from system to the heat sink. Okay, so now we will be having some transfer of heat from system to the heat sink. And after this heat transfer is completed, we will be finding that because of this heat transfer, what will be happening? Our energy content of the system will be decreasing. So because of decrease in energy content of the system, the pressure within the system will also, some momentum of the molecules will also decrease. So because of that, we will be finding that our piston will be moving in downward direction and it will be reaching to its initial position. Okay, so now the piston will be reaching to its initial position and we are having some gas inside, and this gas will be having once again what we will be having, this gas will be once again having the thermodynamic state equivalent to that of state 1. So it means we have returned to the stage from where we have started earlier. Okay, so now in this heat rejection process, let me say that Q2 amount of heat has been rejected. Okay, so you we will be finding that the amount of heat which we have rejected over here, Q2, that will be less in comparison to the amount of heat which we have added during the expansion process. Why? Because during the expansion process, we were raising certain amount of weight also. Okay, so we were spending some amount of energy in raising the weight and some amount of energy was required to expand the gas. So that's why what we were having actually, our Q1 amount will be more in comparison to the amount Q2, because in case of Q2 now, our sole purpose is to bring the system or bring the gas to our first thermodynamic state, initial thermodynamic state. Okay, so now once again, if I have to start this operation in a thermodynamic cyclic manner, what I can do, I have to put this W weight over here and I have to connect this cylinder through some diathermic wall to a heat source. Okay, so once again, I can like go back to my starting point, and from this point actually I can once again start this cycle. Okay, so now during this cycle, if I write over here the first law of thermodynamics, so as per first law of thermodynamics, we know that Q in, summation, or I should write total amount of heat transfer. So del Q minus del W will be equal to, so this is my closed system, so that will be nothing but equal to delta U. Okay, so if I write this first law of thermodynamics for my overall cycle, whatever we have seen, so from the previous diagram, it is clear that my state 2 is equal to, so my state, finally my system has actually reached to state 1. So if I talk about the thermodynamic cyclic manner, my initial and final state will be same. So UF minus UI will be equal to 0. So because of that, delta U for this particular process will be 0. Okay. Now what will be happening? We will be having delta Q as nothing but Q in. So Q in is equal to Q1 minus Q2 minus of, we will be having delta W. Delta W will be nothing but equal to W out minus W in. So W in, because we were not having any weight over here, but still our piston has displaced, so we will be having some small amount of W in also over here. So that is equal to 0. Now we already know that our Q1 is greater than Q2 and W out is greater than W in this particular case. So because of that, what will be happening? I can say that my net amount of heat transfer, whatever we are having, that is equal to nothing but net amount of work done. Okay. And now you can see clearly that whatever the net amount of work done we are getting, that is nothing but equal to Q1 minus Q2. Okay. Where Q1 was the amount of heat which is added to the system. So Q1 is amount added to the system and Q2 is amount which is rejected from the system. So it means one important point we can see that while we are having a heat engine, if we are adding Q1 amount of heat in order to obtain some work output from the system, what will be happening? The entire amount of heat will not convert into work because we will be having some heat rejection also, and this heat rejection has to be done in order to operate our thermodynamics system in a cyclic manner. Okay, so this is one very important point. We have seen that our W net, which is a positive quantity, equal to Q1 minus Q2. This Q1 minus Q2 is also once again a positive quantity. So it means what we are having, that with the help of this heat engine, we are able to operate our system in nothing but thermodynamic cyclic manner, and we were able to have positive work and positive heat interactions. Okay. However, one important point we have to see, the point is that we had supplied Q1 amount of heat, but that entire Q1 amount of heat has not converted into W net amount of work. Rather, we are having some heat rejection also. Okay, so our Q1 is nothing but equivalent to W net plus Q2. So it means we cannot convert 100% of the heat into equivalent amount of work while we are operating our system in an thermodynamic cyclic manner. Okay, so that is one important conclusion which we can make over here. If we have to operate a system in a thermodynamic cyclic manner, we cannot convert 100% of heat into equivalent amount of work. So that's why we call heat as nothing but as low grade energy or low quality energy. So heat we call as nothing but low grade or low quality energy. So this is where actually the quality comes into picture. Okay, so because we cannot convert the amount of heat which we are supplying to system in complete amount of work, okay, equivalent amount of work while we are operating our system in an thermodynamic cyclic manner. So that's why heat is considered as low grade energy or low quality energy, because if we are operating in a thermodynamic cyclic manner, we have to reject some Q2 amount of heat. Okay, so this particular statement actually becomes the basis for second law of thermodynamics. Okay, so second law of thermodynamics we'll subsequently see. Now the device, so heat engine is nothing but, we have got on common definition. So heat engine is nothing but a device which convert heat into work. Okay, so that is something which is seen, that while we are converting heat into work, we are calling that device as nothing but our heat engine. If you want to see the practical examples of heat engine, we are having a wide range of practical examples available for heat engine. So if you talk about your steam power plant, so in case of steam power plant, what we do, we are having actually energy of the coal or the liquid fuels, which is actually added, and that energy is added into our working medium, where our working medium is nothing but water, and that water we convert it into high pressure steam, and then high pressure steam is actually expended over the turbine, where we get some amount of work in terms of soft work, and that work is further converted into electricity with the help of generator. Okay, so in case of thermal power plants, coal based thermal power plants, actually what we are doing, we are converting the heat energy, because while combustion of the coal and air is happening, we are getting actually energy in the form of heat energy. Okay, so by using some mechanical arrangement, we are converting that heat energy into work output. So that's why we can say that our steam power plant is nothing but a heat engine. Okay, so apart from that, we are having IC engines, internal combustion engines, which are used in automobiles, where we are adding gasoline and diesel as our fuels, and many times now we are having CNG engines also available. So we are adding some gaseous or liquid fuels, and these gaseous and liquid fuels are actually converting energy, producing heat, and that heat actually further then being converted into mechanical work. Okay, so any device which convert heat and into work, we say that device has nothing but our heat engine. Okay, so now what I will be doing, I'll stop at this point and we will further continue our discussion in our next lecture. Okay.
So please give some directions.
Now, do you have lecture at 11?
Excuse me, sir. So please give some directions.
Yes, sir.
Sir has
Yes, sir.
uploaded the lecture, I think.
Yes, sir,
So
we
we
have
will have to
lecture.
see.
Yes, sir. We have to.
Yes, sir.
You are having lecture at 11 or not?
Yes, sir.
Yes, sir.
Yes, sir.
Sir, why we had removed that W weight from the exam
Yes,
that
sir.
you